Okay, hello everyone. It seems like it's now 12, so we're gonna start the presentation now.
Yeah, I didn't expect that many to be present. Hi everyone. Today, me and Arian are excited to talk about a cool research paper, which is about encoding sequential information in semantic space model. We're diving into two methods: holographic reduced representation (HRR) and random permutation (RP). Which is going to handle info in semantic space models. Okay, yeah. Now, that in semantic space models represent words or concept in multidimensional space where their relationships are captured based on meaning. The purpose is the purpose here is to facilitate the understanding of words, concepts, or relationships.
Yeah, sorry, I spent a lot of time on this. I just wanted to understand so basically.
Please mute your microphones while we present. Thank you.
And enable effective processing of sequential information. Words or concepts are represented as vectors in high-dimensional spaces, and the proximity in space implies similarity in meaning. We see here also that semantic relation capture the relationship like synonymy and antonymy and contextual relevance. We have the Bagel model here. The Bagel stands for bound encoding of the aggregate language environment. The model analyze and process a large amount of text, sentence by sentence. Each word is assigned a representation, and this representation evolves based on the words that often appears together with it. Words that tend to appear in sentence alongside the target word influence and shape its representation. Additionally, words with similar contextual usage pattern contribute to shaping the representation of the target word. Words are represented as we said by high-dimensional holographic vectors. The first encounter assigned a random environmental vector. The environmental vector EI remains constant throughout subsequent encounters. MI memory lexical vector undergoes changes each time the word is encountered, adapting to a new context. When a word I appears in a sentence of n words, a context vector CI is formed by summary environmental vectors, e.g., which for all the words in the sentence, excluding the target word itself. The word's lexical representation MI is updated by using superposition method. MI undergoes an update throughout the superposition. We have here a common we have it here an issue that common words like a, the, of, etc. can mix up our word memory because they are everywhere. So should we get rid of those common words? Well, here the solution is to use a stop list to ignore these common words when when figuring out a word's context. For example, here we have this meaning, and without using the stop list, we have the context for the context vector for dog. It's like summing all those vectors for those words, but with getting rid of the common words, we get this one instead. But here we have another issue that context vector for this sentence will be the same as this, although it's not they are not quite have the same meaning here. Here we shows that without stop list we have this sentence, and with stop list we got this sentence instead. We want to know where a word is word sits in a sentence. Is it at the beginning, middle, or end? We use something called directional circular convolution. Think of it like a way to connect a word to all the nearby word chunks in a sentence. Each word gets a special order vector, like a fingerprint. The vector depends on its position, and the n-grams chunks it's part of it. It's part of. The P is the position of the word in the sentence. The lambda here, this simple, a parameter tuning how much we care about the word's position. We use constant random placeholder vector, this symbol phi, and through some math magic we get the order vector by using this formula. The purpose helps us keep track of word order in a sentence, making sure we don't lose the valuable information. Here we illustrate circular convolution. We have this sentence. We get by using the convolution, we connect words in a sentence and capture their relationship. We have those from this sentence. We get bigrams, trigrams, quadrigrams, and we get the order vector for the dog by summing up all those together. The purpose helps us to create an order representation for each word in the sentence. In the sentence. Okay. Go into next. Oh, yeah. MI is updated using a combination of context vector CI and order vector OI. MI gets enriched by considering the current sentence context and words order. This sum ups across all the sentences where the word has been encountered. Then the new MI becomes a composite lexical vector, capturing the word's meaning, context, and order information across various sentences. The dynamic update allows us to adapt and refine our understanding of a word of a word as it appears in different contexts over time. We see this example. We by using the returning order information for in the Bagel model, we could guess the next words, mostly the next used word. Bagel use inverse circular convolution, and this is the formula for it, and this is the symbol for circular convolution here. By summing up all these decoding vectors, give us a vector similar to the pattern of elements in E. Luther, This process showcase Begel's ability to reconstruct meaningful sequence and predict the likely next element in a sequence. And here we extracting order information with resonance. We explore how Begel retrieves order information through resonance. In this example, the encoding vector, this is based on if it's 2 words plus 2 words, the 3 words. The encoding vector is then compared with the lexical vectors m from 1 to n, and the cosine similarity is calculated for each. Words frequently encountered in the blank position during learning exhibit higher relative cosine values with the order vectors. Example here, with the most likely words would be refused in this blank, and went for 59%, went for 57%. This resonance process allows Begel to identify and predict words that fit well into a specific position within a sequence based on the past learning experience.
Okay, now let's talk about the RPM, or the random permutation model. RPM is another SSM to encode sequential information in semantic memory. This just means that those computer models are designed to understand and remember the meanings of words like our brain does. And also, they also pay attention to the order of words to get a better understanding of the language, which is more like how we naturally process language in our daily lives. One more interesting fact is that the term random permutation can be a bit misleading. The permutations used are not completely random in the sense that being unpredictable or different in every time. Instead, they are systematically consistent but applied in a way that seems random compared to the original order of elements. As you can see, the notations are very similar to what we already discussed, so I won't go so deeply into it. Next slide. One of the key challenges in language processing is understanding the order in which words appear. The order of words can significantly change the meaning of a sentence. Take a dog bit the mailman and a mailman bit the dog. Those are two whole different sentences. Random permutations in RPM are used to encode this order information by shuffling the elements of word vectors in a controlled manner. RPM keeps a track of where words appear relative to each other in sentences. Each word in a sentence affects the meaning of the words around it. To keep track of this, RPM applies a specific permutation for each position relative to the word. For an example, the word before might be shuffled in one way, and the word after in another way, and so on. This helps the model to understand not just the word, but how its meaning changes in different contexts. And also you can see in this mathematical formula that pi to the power of -1 is the inverse, and pi to the power of n is the vector is basically permuted n times. Okay. So imagine we have a sentence, the cat sat on the map. That's just an example. We want to encode the context of the word cat using this method. Let's simplify it and say that our vectors are just numbers to make it easy to understand. Each word is represented by a unique vector, numbers in this case. So the is number 1 because it has the index of 1. Cat has the index of 2, so it's 2. And sat and has 3, and so on. Now we use a permutation to encode the position of these words relative to cat. Let's say our permutation function, pi, as we saw from the last function, just adds 10 to the number, and its inverse subtracts 10. then the encoding for the cat will look something like this, where 1 is the index, and then we take the inverse function because it's the previous word of cat, and that's why we subtract it by 10, which we get 9 from. And then cat in by itself has no permutation, so we just leave it at 2. Sat has 3, and we add 1 permutation, so it's 13, and so on. So the encoded vector for cat would be something like -9 to 13, 24, and so on. In a real-world scenario, these vectors would be much more complex and than simple numbers. And the permutation function would be much more complicated than just adding or subtracting certain numbers. But the key idea is that this method encodes the position of words relative to the target word, cat in this case, in a way that can be mathematically manipulated. Next slide.
Jag vet inte, det är trögt. Jag trycker på. Det går inte att växla.
Oh, there we go.
Yeah.
We're now going to go a little bit deeper into the key differences and similarities between the two influential models in the world of semantic space models, the Beagle model and the random permutation model, or RPM. First, let's briefly recap what these models were about. The Beagle model is known for its use of holographic reduced representation, aka HRR. It's a complex way of representing semantic relationships between words, taking into account their co-occurrence in sentences, and so on. RPM introduces a novel approach by using random permutations to encode the order in which words appear. Now let's just compare these two. Okay, so one of the most significant differences lies in their computational efficiency. RPM, with its use of random permutations, is generally more efficient, especially when dealing with big data sets. This efficiency is very important for processing big text corpuses like Wikipedia or large libraries. We will discuss this a little bit later. So while both models' goal is to capture the word relationships, RPM stands out for its ability to encode sequential order of words more effectively. And when it comes to scalability, RPM again has the edge because of its efficient handling of large data sets. Yes, so that was that. Okay, so here we can see a little bit of a demonstration of how efficient RPM is on larger data sets. As you can see, so both of them, when given lower or smaller data sets, perform just as well, given like a higher dimension. But you can see that Beagle performs often worse than RPM, or the same, when it comes to bigger data sets. So that's why RPM is so efficient. Okay, next. So experiment 2. In this experiment, the context information was deliberately omitted to focus solely on how each model encodes order information. When we compare the performance of HRR and RPM models, there were no significant differences in their performance on a smaller dataset, as we mentioned earlier. This means that both models are equally capable of handling ordered information in linguistic data on a smaller scale. But a big distinction became clear when it came to scalability. Only the RPM model was able to scale effectively on the full corpus of data. This ability to handle larger data sets is a very large advantage, especially in real-world application when it comes to massive amounts of text that needs to be processed, which is often the case. Yes, next slide. So this is just the information about, the findings. Next one. So in this experiment, experiment 3, the experiment utilized convolution in Beagle and random permutations in RPM as they were originally designed. Also, they maintained context vectors in both models and employed a sparse temporary ternary vector representation specifically for RPM. The primary goal here was to observe how each model performs in processing and analyzing linguistic data. They particularly focused on how well they handle tasks related to semantic relatedness. Basically, how they understand and represent the meaning and relationships of words within a text corpus. The findings are that on a smaller subset of Wikipedia data, both Beagle and RPM showed similar levels of performance. Yes, so this means that on a smaller scale, both models are equally good at processing linguistic data and understanding semantic relationships. But a noticeable difference was shown when the models were applied to an entire Wikipedia corpus. Only RPM was able to scale effectively to this much larger data set. Like I mentioned before, this scalability of RPM is very, very beneficial. This result highlights a key strength of the RPM model. So yeah. So this is the results they acquired from the test. Next one. Okay, so experiment 4. The key change in this experiment involved modifying how RPM typically works. Instead of using its standard random permutation function, they implemented a random connection between nodes without requiring each node to be unique. So basically, they shifted from systematic shuffling method to more chaotic one, a free-form connection pattern. The results showed that there were no consistent advantage of using random permutations, RPs, over these randomly connected nodes, RCS. This means that the specific method of shuffling or connecting nodes might be more flexible than previously thought. But a big downside to using RCs was found. They lack exact inverse function, which means that it's more challenging to reverse the process and retrieve original information, which is very crucial in the models. Another limitation they observed with RCs was their potential to fail in scenarios involving low-dimensional vectors or long chains of words. So here are the findings they got. Next. So both HRR and RPM have shown similar performance levels when trained on smaller datasets. This similarity indicates that both models are very competent in handling semantic tasks on a manageable scale. A standout observation is the higher scalability of the RPM model. It demonstrates amazingly efficient and effectiveness when applied to a larger dataset, a critical aspect for practical applications in processing extensive linguistic data, such as Wikipedia data. The experiment also highlighted the potential flexibility of the applications of random permutation. By relaxing the uniqueness constraint in RPM, we could achieve results that closely fit human data. They presented this model as psychologically plausible components of a theory of semantic representation. And that would be all. Thank you very much for participating. We appreciate everyone. And we are open for questions now, if anyone has any.
Hi guys, Evgenius here. Thanks for presenting. So it was a good summary of this paper. And I think it was a really nice extension to what you have learned in Lab 3. So if you relate to Lab 3, so this is my question. So, I mean, what are your reflections? I mean, how this paper relates or extends the stuff that you did in Lab 3?
I'm sorry. Yeah, continue.
Yeah, I believe it's more in Lab 3. Here we deep more in how Beagle works and the other and the two other methods. In Lab 3 we all it's a bit similar to what we did in Lab 3. So Is that any like concrete question or?
Yeah, it is exactly the stuff that you did in lab 3, actually. I mean, this with the random permutation. So it and as I said, so it extends the information there. So with for example, so showing how you can do similar stuff with say real valued vectors. So using holographic reduced representation. So that's convolution. So the role of convolution, circular convolution there, is exactly well. It plays similar role or as the permutation. So it's actually pretty much similar.
Yeah.
Just a comment. So it's maybe it's not much of a question, but more of a comment. So consider.
Okay. Do we have any more questions? Okay. Seems that we don't have any. Thank you very much for coming to our presentation. And yeah.